Welcome back. Today we're starting our deep dive into transfer architectures. First question: what exactly is a transfer architecture?
Transfer architecture refers to the design patterns and techniques for adapting pre trained foundation models to new tasks and domains.
It's about the architecture of transfer itself, how we structure the adaptation process, not just the base model architecture.
Think of it as the engineering of reuse. How do we efficiently and effectively transfer learned capabilities to new applications?
We've already discussed transfer learning conceptually. Now we're getting into the specific architectural approaches.
Let's start with the most straightforward approach full fine tuning with task specific heads.
You take your pre trained model, add a small task specific layer on top, and fine tune the whole thing.
For classification, this might be a linear layer that maps from the model's hidden dimension to the number of classes.
For generation tasks, you might just use the language modeling head that's already part of the model.
The advantage of full fine tuning is that it can adapt the entire model to your task, potentially achieving the best performance.
The downside is cost. You need to store and update all parameters, which requires significant memory for gradient computation.
For a 7 billion parameter model, you might need 100 plus GB of GPU memory to fine tune with standard methods.
This brings us to parameter efficient fine tuning, or PEFT, which we'll dive deeper into in the next episode.
PEP methods modify only a small fraction of parameters while keeping most of the model frozen.
This dramatically reduces memory requirements and training time while achieving competitive performance.
Another transfer architecture approach is adapter modules. These are small neural network layers inserted into the pre trained model.
The original model parameters stay frozen, only the adapter parameters are trained.
Adapters typically use a bottleneck architecture, project down to a lower dimension, apply nonlinearity, project backup.
This allows task specific adaptation with minimal parameters. You can train different adapters for different tasks and swap them as needed.
Prompt based methods are another category of transfer architecture.
Instead of modifying the model, you modify the input. You prepare task specific prompt text that steers the model toward desired behavior.
Prompt engineering is the manual version, carefully crafting prompts through trial and error.
Prompt tuning is the learned version. You treat the prompt as continuous embeddings and optimize them.
These soft prompts aren't real text, they are vectors in the embedding space that the model can condition on.
Prefix tuning is similar but adds trainable vectors to every layer, not just the input.
These methods are extremely parameter efficient. You might only tune 0.1% of the model's parameters.
Let's talk about architectural choices for multitask transfer.
One approach is separate heads. The backbone model is shared, but each task has its own output layer.
This allows the model to share representations while maintaining task specific decision boundaries.
Another approach is text to text framing used in T5. All tasks are cast as text generation.
Translation, summarization, classification, everything becomes read input, generate output text.
This eliminates the need for task specific architectures. The same model structure handles everything.
For domain adaptation, the transfer architecture often involves intermediate adaptation layers.
You might do continued pre training on domain data, then add domain specific fine tuning.
Some approaches use domain discriminators, auxiliary networks that help the model learn domain invariant representations.
The idea is to learn features that work across domains rather than overfitting to source domain specifics.
Let's discuss mixture of experts as a transfer architecture approach.
MOE models have multiple expert networks. A gating mechanism routes different inputs to different experts.
This allows specialization. Different experts can handle different types of inputs or tasks.
For transfer, you might freeze the shared components and only train task specific experts or learn new routing patterns.
Another architectural pattern is hierarchical transfer.
You might first adapt to a related intermediate task, then adapt again to your target task.
For example, adapt a general model to medical text, then to radiology specifically, then to a particular radiology task.
This stepwise refinement can improve performance when tasks have natural hierarchies.
Let's talk about modular transfer architectures.
The idea is to decompose the model into composable modules that can be mixed and matched.
You might have separate modules for different skills, reasoning, knowledge retrieval, code generation, etc.
Different tasks use different combinations of modules, and you can transfer modules across models.
Knowledge distillation is another important transfer technique.
You train a smaller student model to mimic a larger teacher model.
The student learns from the teacher's output distributions, which contain richer information than hard labels.
This allows you to transfer the teacher's capabilities to a more efficient student.
The student model might have a different architecture, fewer layers, smaller hidden dimension, or more efficient attention.
Distillation is a form of architectural transfer, transferring capability from one architecture to another.
Let's discuss cross-lingual transfer architectures.
Multilingual models trained on many languages can transfer from high resource to low resource languages.
The architecture typically uses shared subword vocabularies and shared parameters across languages.
Language specific adapter layers can be added for better per language performance while maintaining shared representations.
Another consideration is memory efficiency in transfer.
Techniques like quantization can reduce model size using 8-bit or 4-bit weights instead of 32-bit.
QLoRa combines quantization with LoRa for parameter efficient fine tuning, enabling fine tuning of very large models on consumer GPUs.
Pruning is another approach, removing weights or even entire neurons that contribute little to performance.
This can significantly reduce model size and inference cost while maintaining most of the capabilities.
Let's talk about continual learning architectures.
In continual learning, the model learns new tasks sequentially without forgetting previous ones.
This requires architectural choices like progressive networks, where you add new modules for new tasks while freezing old ones.
Or elastic weight consolidation, which identifies important weights for previous tasks and protects them during new task learning.
Continual learning is crucial for real world deployment where models need to adapt to new data and tasks over time.
Finally, let's touch on meta learning architectures for transfer.
Meta learning, or learning to learn, trains models to quickly adapt to new tasks with minimal data.
Architectures like MAML learn initializations that are good starting points for fine tuning on new tasks.
This is different from standard transfer learning. You're explicitly optimizing for transferability.
So, to recap, transfer architectures include full fine tuning with task heads, parameter efficient methods like adapters and prompt tuning, multitask architectures with shared backbones, modular and hierarchical designs, distillation for architectural transfer, and specialized approaches for continual and meta learning.
The choice of transfer architecture depends on your constraints, data availability, compute budget, number of tasks, and performance requirements.
Next episode, we're diving deep into domain adaptation techniques, how to specialize models for specific fields.
Thanks for listening.
Until next time, keep learning and stay curious about AI.